I think we can start. So, in the last lecture, we started talking about Metropolis algorithm, and we did discuss Metropolis algorithm. The video is not yet uploaded. I will upload it from last lecture, that is Thursday. So today we are going to wrap up our discussion on Metropolis Hasting, which is an extension of Metropolis algorithm. So we'll talk about limitations of Metropolis algorithm, and from there we will go into the Metropolis Hasting algorithm. Okay, and we'll also be talking about Gibbs sampling, which is another type of MCMC algorithm. So remember, Metropolis algorithm, Metropolis Hasting algorithm, and Gibbs sampling, all of these three are MCMC algorithms. So MCMC is a broad class of algorithms, and these are kind of specific algorithms within the MCMC group or class. Okay. So to quickly review, these are things we have already covered since the exam is on Wednesday. So let me just quickly review what are the sampling methods we have covered till now. If you remember, we started with reverse sampling or inverse PDF or inverse CDF. But we said that that is not very useful because the CDF or the PDF for us is not known, and so forget about inversing that. And it is not known because the normalizing constant is not known, correct? So then we started talking about sampling that are actually useful and can actually be used for finding the posterior. And there we talked about, first of all, rejection sampling. From rejection sampling, then we talked about importance sampling. Rejection sampling, samples were getting rejected. Importance sampling, all samples were used, but with some weights. And then we went into Markov chain Monte Carlo, where we talked about Markov process, Markov chain, and the state transition diagram, transition probability, transition matrix, and transition kernel. And using those things, we said that you can use that also to sample, and in the Markov chain Monte Carlo case, the samples you are drawing are not independent. The next sample is a function of the previous sample in the generic sense. Okay. And in Markov chain Monte Carlo, we have, in the last lecture, we talked about Metropolis algorithm, and we concluded our discussion on the Metropolis algorithm. Very quickly, this is the Metropolis algorithm that we discussed. So the idea is it is kind of motivated from rejection sampling. You will see that there is an acceptance ratio. But here, when you are rejecting something, it's not just getting rejected, it's just basically you are retaining the previous sample. So that is the difference. In rejection sampling, when you reject, it's rejected. There is nothing, you are not getting a sample. In Markov chain, even when you are rejecting, you are getting a sample, and that sample is your previous sample. And that's what you see in the last line, where xn plus 1, if you reject it, will become equal to xn, or it will accept the proposal, which is 1. Okay. So that is one major difference with rejection sampling. So it's not rejection sampling, but it's motivated. So there is some similarity you will find. Okay. But there is a limitation of Metropolis algorithm, which is the requirement for symmetric proposal. So the qy given x is your proposal, and it has to be symmetric. If your proposal is not symmetric, this algorithm fails. And when I say it fails, it does not satisfy the 3 criteria we talked about last time. And the 3 criteria were irreducibility, then aperiodicity, and the most important one, pi invariance. But we don't do pi invariance, we do a detailed balance. So, and you can clearly follow that when I proved that the transition kernel of Metropolis algorithm satisfies the pi invariance or the detailed balance condition, I did use the symmetry. Had I not used the symmetry, it would not have been possible for me to prove that, which clearly shows that symmetry is a necessary condition, and that's a limitation also. So now, with this background, Hasting actually improved upon the Metropolis Hasting algorithm. It was Hasting who improved upon the Metropolis algorithm so as to allow any arbitrary proposal. Okay, so it was Hasting who improved. So, Hasting improved the Metropolis algorithm so as to allow arbitrary is not the correct one, I think generic is the correct terminology, generic proposal. Okay. So what we will do is, we will first go through the steps of the algorithm of the by the way, this algorithm was then known as the Metropolis Hasting algorithm. And remember, last time I said that Metropolis algorithm was proposed around 1950. Markov chain was proposed around 1908. So it took 15 years to go from Markov chain, which is the fundamental thing, to Metropolis algorithm, which is now an algorithm that uses Markov chain. And then it took another 20 years to go from a symmetric proposal to a generic proposal. So Hasting proposed it around 1970. I don't remember the exact year, but 1970, 1972, something like that. So it took another 20 years for Hasting to actually address the limitation of the Metropolis algorithm. And Metropolis Hasting algorithm was declared to be one of the top 10 algorithms of the 20th century. So from 1900 to 2000, that is the 20th century, one of the top 10 algorithms of that time was the Metropolis Hasting algorithm. Some of the other algorithms that were there was, for example, the Fourier transform, the first Fourier transform algorithm. Then there was the expectation maximization algorithm, which we probably will talk about sometime later. And like that, there were others also. Okay. So, and it has huge application, and that is the reason it became one of the top algorithms. And you will find application of Metropolis Hasting algorithm in different domains, starting from molecular dynamics to statistical mechanics, which is same actually, to statistics, statistical computing, to so many things. There is, I mean, and the most important and interesting fact is that even today people are coming up with algorithms which are improvement over Metropolis Hasting. So it is relevant even today. For example, I think around 2014 or 15 or maybe 16, there was a algorithm that was proposed which was known as the NICE MC algorithm. NICE, NICE hyphen MC is Monte Carlo algorithm, where the idea was it was the Metropolis Hasting algorithm, but the proposal was coming from neural network, GAN. So NICE MC is again a Metropolis Hasting algorithm, an improvement to that, which was proposed in 2015, 16, 17 I'm talking about. And even today if you search, you will find improvement to this that are being proposed, because it has such huge application that any improvement will have a huge impact to various domains. So that is the reason. So, okay, with that background, let us go to the algorithm and see how Metropolis Hasting algorithm is different from the Metropolis algorithm. Okay, so we'll just write the algorithm first, and then we will see that how things are getting, how it is different from Metropolis, and how the criteria are getting satisfied. The three criteria, which are the pi invariance or detail balance, and irreducibility and aperiodicity. Okay. So let me write down the Metropolis Hasting algorithm. Metropolis Hasting algorithm. So it is very rare for anyone to write the total name. Everyone knows this as the MH algorithm. I mean, everyone understands that MH is Metropolis Hasting. Like I said, EM is expectation maximization, but EM is what everyone knows. Okay. So what I will do is that instead of Metropolis Hasting algorithm, I will write down the steps of Metropolis algorithm first. And then I will change color and I will write the modification with another color just to show the contrast between the two algorithms. Okay. So Metropolis Hasting algorithm. I am writing the Metropolis algorithm, remember that, not the Hasting yet. So, input. What were the inputs of the Metropolis algorithm? Can you remind me? What were the inputs? Proposal, okay, which is Q, and the chain of the, the length of the chain N, right? So your input is length of the chain, which is N, and proposal, okay, and proposal we denoted it as Q Y given Xn, okay, or maybe Xt. Last time I think I used Xt. N I am already using, so that's confusing. Let's write Xt. Okay. Now, how Metropolis algorithm is initiated? What was the first step? You will have some initial starting point, and it is independent of the initial starting point. It can be a deterministic point, it can be some sample, does not matter in the long run. Okay. So step 1 is you have x naught, xt is equal to x naught, and I am not writing it, but remember that x naught can be a deterministic number that you are providing, or it can be some sample from some distribution, right? Then what is the next step? You will draw samples, you will draw the proposal, and you will draw a uniform sample in 0 to 1, right? So step 2 was you will draw a sample y from Q of y given xt, and you will draw a sample u from uniform 0, 1, right? What is the step after that? In Metropolis, I am not even talking about Metropolis Hasting. So this we have done last time. So what is the step after that? Correct. You calculate the acceptance ratio. So that I am going to do in the next page. So step 3 is you will calculate acceptance ratio between or going from xt to y, and this was equal to, what was the acceptance ratio? Pi of y divided by pi of xt, and which is equivalent to pi star of y divided by pi star of xt. I am writing pi, but they are same because z and z will cancel out, okay, because both are the same distribution. So acceptance ratio is minimum of 1, pi of y divided by pi of xt, right? This was the acceptance ratio, correct? And I can write pi star and pi star because pi is pi by z, pi star by z, so z and z will cancel out, okay. Step 4, what was it? The if condition come into picture, and you are going to check whether the acceptance ratio is less than or greater than the uniform sample you have drawn, following the rejection sampling logic. So if u less than equal to a xt comma y, then you set xt plus 1 to be equal to y, else okay, with probability a xt comma y, else you will set xt plus 1 to be equal to xt, and you repeat it until the length of the chain. This is just one, this is for n equal to 1 I have done, and you repeat the process for n up to n equal to n. Now the initial few samples you are going to reject, that is the burn-in period, and the rest of the samples are samples from your target distribution. So this is the Metropolis algorithm, I just repeated it. One thing I did not write, so let me write it. Proposal is this, and in Metropolis this was supposed to be symmetric. In Metropolis, that was the condition, by the way, right? So now, what I am going to do is that I am going to modify this algorithm, and the modifications will be in black, and I will do the modifications which Hasting suggested, and that will make the algorithm, that will justify the name. The name is Metropolis Hasting algorithm, not Metropolis. So what I have written now is the Metropolis algorithm. So first thing I will do is, this is not needed. No longer you need Q to be symmetric, okay? Because that's the main contribution of Hasting, that you can work with any general distribution. Second thing, this acceptance ratio is modified. This becomes Q xt given y, you multiply with it, and here Q y given xt. Maybe I should remove the red and then, okay. So what Hasting suggested was that you just change the acceptance ratio, and that's all. This is your Metropolis Hasting algorithm. So the change is minimal. You can use any arbitrary Q if you calculate the acceptance ratio by using this formula, or basically this additional factor if you include. That's all. And what is it doing if you think of it carefully? If it is symmetric, then this will cancel out. The black one will come out to be 1, and you go back to the Metropolis algorithm. Because if it is symmetric, then Q of y given xt is equal to Q of xt given y. So that will cancel out, and you go back to the original Metropolis algorithm, right? Clear? So this is the Metropolis Hasting algorithm. Any doubt on the algorithm or the changes? Easy to follow. So basically, if you can write a code for Metropolis, you can write it for Metropolis Hasting. That's all. Okay. Now, I have made a modification. Okay. Now I said there are 3 criteria, right? That the transition kernel should satisfy. What were the 3 criteria? The first one was pi invariance or detail balance. The second one was irreducibility. Third one was aperiodicity. Now in Metropolis algorithm, not Metropolis Hasting, in Metropolis algorithm, how was aperiodicity satisfied? Can you remind me what was the logic we gave in the last lecture in support of the fact that the transition kernel in this case satisfies the aperiodicity? Do you remember? What was the logic? Correct. The logic was that even if the samples are coming in a periodic manner, there is a finite probability with which a sample will be rejected. So that means the samples that will ultimately get will not be periodic. And the example I gave was that suppose a sample is appearing in the first time, 5th time, 9th time, 13th time from the proposal. So there is a periodic nature. Every 4 times the same sample is coming. But sample means proposal, y. But even if the same y is coming 4 times, I mean after each 4 times, it is possible because of this acceptance criteria that will be accepted 1 time, 3 times it will be rejected, or 3 times it will be accepted, 1 time rejected. So and that will break the periodicity. So the fact that a sample can be rejected with a finite probability ensures that the final samples you are getting is aperiodic, or the fact that a proposal is getting rejected with a finite probability ensures that the final samples you are getting is aperiodic. Clear? So this is the same thing we discussed last time. Same thing holds here. Nothing has changed. It's still a finite probability with which you are accepting, which means it's still a finite probability with which you are rejecting. Clear? The second condition was irreducibility. In Metropolis algorithm, what was the logic we gave, or how did we ensure that irreducibility is satisfied? Irreducibility is that you should be able to reach starting from any state, you should be able to reach all other states with a finite probability, right? So what was the logic that we gave last time? That in support of the fact that the transition kernel will satisfy the irreducibility criteria, we said that the irreducibility criteria can be trivially satisfied if we select a correct proposal. For example, if my proposal is Gaussian varies from minus infinite to plus infinite. That means I can reach or draw any sample with a finite probability. Even if I say select uniform, even in that case, because it is y given xt, each time it will move. It's a window kind of thing that will move. And as a result, even in that case, most probably it will be satisfied. But generally, we take Gaussian proposal or random walk proposal. And in random walk means it's your previous step plus a Gaussian noise. So as soon as you add a Gaussian noise, it goes from minus infinite to infinite. Gaussian, the range of x is minus infinite to infinite. Right? As a result, it's always irreducible. You can draw any sample with a finite probability. Okay? Clear? The last one and the most important one was the detailed valence. And that we did prove, right? We did prove that. So even in this case, we need to prove that, right? So let's talk about the detailed valence criteria. So before we talk about detailed valence criteria, let us talk about what is the transition kernel in this manner, in this case. Or that's what's the transition kernel for MH is. So tell me, what is the transition kernel of going from xt to xt plus 1? Remind me, how did we calculate it last time? It will be exactly same. Nothing will change. So how did we calculate the transition kernel? Is the proposal the transition kernel? No, right? Because not every time the proposal is accepted. So how did we calculate it last time? We said that xt plus 1, what is transition kernel? It is probability of xt plus 1 given xt, right? And we said that we can reach xt plus 1 from xt in two ways. One, if my sample is accepted, or if my sample is rejected. Correct? If my sample is accepted, then what will be the probability? First, I will draw sample xt plus 1 given xt multiplied by a xt to xt plus 1, right? This is the case when it is accepted. So you are drawing a sample from q of xt plus 1 given xt and accepting it. Plus the case when it is rejected. Now it can be rejected in n number of ways or infinite number of ways, because you can draw a y. If that y does not satisfy the equation 4 or the step 4, then it gets rejected. If it does not satisfy the if condition, it gets rejected. So that can happen for multiple number of y's. So that means let's just write, so that's why the integral sign. So what you will do is that integration, you will draw a y from, q of y given xt, and then reject it with probability xt comma y, and this is for all possible y. I repeat, although we did it last time, let me repeat it. So the transition kernel is the probability of xt plus 1 given xt. Correct? Now that is equal to, from the algorithm, you can reach xt plus 1 in two ways. One, by accepting a proposal, or by rejecting a proposal. If you accept a proposal, in that case your proposal is your xt plus 1. So it is q of xt plus 1 given xt multiplied by the acceptance ratio with xt plus 1 in place of y. Right? The second case is you have rejected it. And if you reject it, then it is equal to integration of y given xt now. because, and that can be many y's, so that's why the integration over y multiplied by the that sample is getting rejected. So that becomes your transition kernel, right? Clear? Any question on this one? This is a repeat from last time, but still if there is question you can ask, because this is very important. Why? Correct. What is xt plus 1? xt plus 1 is the next sample, right? So now look at step 4. What can xt plus 1 be equal to? If it is accepted, it will be equal to y. If it is rejected, we are not throwing away the sample. Even still in that case, we are getting a xt plus 1. That is equal to xt. So we are considering it because in Metropolis Hasting or Metropolis algorithm, even in rejection, we do get a sample. So that's why. If it was rejection sampling, then we would have not gotten a sample. And in that case, things would have been different. Okay. Clear? Okay. So now, this is my transition kernel. And we need to show that this transition kernel satisfies the detailed balance condition. So, to show k xt comma xt plus 1 satisfy the detailed balance, I am writing as dB. Detailed balance has another name, by the way, I did not mention it last time. It is also known as the reversibility condition. Okay, detailed balance has another name known as the reversibility condition. Satisfy the dB criteria, dB condition. And what is the dB condition? We need to show the exact dB condition, which is pi of xt multiplied by k of going from xt to xt plus 1 is equal to pi of xt plus 1 multiplied by k of going from xt plus 1 to xt. Okay. So this is the detailed balance condition, and by looking at this equation, you know that why it is called the reversibility condition, because it's basically reversing xt and xt plus 1, right? So now we'll take the left hand side, substitute k from previous slide, and try to prove that we arrive at the right hand side. Simple. So consider the LHS. If you consider the LHS, I have pi of xt multiplied by, I have k of xt comma xt plus 1, which is equal to, from previous slide, q of xt plus 1 given xt multiplied by a xt comma xt plus 1 plus integration q of y given xt multiplied by 1 minus a xt comma y dy, right? I have just substituted k of xt comma xt plus 1, this expression at the bottom, into the left hand side of the expression. That's all I have done. So basically I have substituted, let me call it equation 1 into equation 2, if I give the naming, right? And then, like last time, what did I do last time? Can someone remind me what did we do? Because we are going to do the exact same thing. If you remember, what we did was, we considered it in parts. We considered the acceptance part and the rejection part and worked with them separately. Same thing we are going to do. So this is equal to pi of xt multiplied by q of xt plus 1 given xt multiplied by a of xt comma xt plus 1. Right? This is the first term multiplied with, I've opened a bracket, plus pi of xt, and then integration q of y given xt 1 minus a of xt comma y dy. Right? Clear? Now, last time I did it in two parts. This time also we will do it in two parts. But can someone tell me what is the second part representing? What is the second line representing? That is the second part. What is the second line representing? What scenario is it representing from the algorithm? Rejection. So when we reject, what happens? xt plus 1 is equal to xt. So the second term is denoting rejection, correct? And when we reject, xt plus 1 becomes equal to xt. So that means wherever there is xt, I can replace it with xt plus 1, right? And that is exactly what we did last time. And if I substitute xt plus 1 there, what will I get? So let me do it once more. So look in this part, right? This part correspond to rejection, and in rejection we have xt plus 1 is equal to xt. So therefore, we can substitute xt plus 1 in place of wherever there is xt. So therefore, we can substitute xt is equal to xt plus 1. Correct? Clear? So what will I get if I do that? We'll do that later. But basically we'll realize that we'll get the right hand side component. Okay. But the first term is still remaining. What is the first term corresponding to? Acceptance. And in acceptance, xt plus 1 is not equal to xt. So we cannot use this logic there. That means we have to show it mathematically. Okay. So therefore, we consider the first term. Let us consider the first term. Okay. And what we have is pi of xt multiplied by q of xt plus 1 given xt multiplied by a. And what is a? What is the formula for a? Minimum of 1 comma minimum of 1 comma pi of y by pi of xt q of xt given y multiplied by q of y given xt. Okay. Correct? Clear? What will we do? We'll push whatever is outside inside the minima. So what will I get if I push whatever is outside inside the minima? This is equal to minimum of, the first term was 1. I have pushed whatever is outside inside. So what will I get? Okay, there is one mistake I can see. Can you tell me the mistake? Repeat. It should be, there is no y here. Here y is equal to xt plus 1. So that is the mistake. So wherever you see y, there is no y in the acceptance. It is xt plus 1. So I have to correct it. Let me correct this part. Okay. So this is equal to pi of xt plus 1 by pi of xt q of xt given xt plus 1 divided by q of xt plus 1 given xt. Okay. Now this is correct. So I have pushed whatever is outside inside. So what will I get? What is the first term? There is 1. 1 will be replaced by pi of xt q of xt plus 1 given xt. So minimum of pi of xt q of xt plus 1 given xt. What will be the second term? Tell me. The second term, pi of xt plus 1 multiplied by q of xt given xt plus 1. The denominator basically cancels out. Correct? Clear? Now we will take the second term outside the minima. If I take second term outside the minima, what will I get? Pi of xt plus 1 q of xt given xt plus 1 minima of 1, okay, let me write the ratio first, pi of xt divided by pi of xt plus 1 q of xt plus 1 given xt divided by q of xt given xt plus 1, right, comma 1, right. Now what is that quantity? Acceptance ratio of what? xt plus 1 comma xt. So it is reversed. So this is equal to pi of xt plus 1 q of xt given xt plus 1 multiplied by acceptance ratio of xt plus 1 to xt. Okay. Correct? So now I will go ahead and substitute this term in place of the first line in the x, right? And I will substitute xt plus 1 in place of xt in the second line. Okay. So basically, I am going to use this and this. Okay. And both of this will be substituted into this expression. The second sentence, the second equation will be follow the first one here, and the first one will follow this one. Okay. So therefore, what will I get? You tell me. So therefore, pi of xt k xt comma xt plus 1 is equal to the first, I will get this one. So this is pi of xt plus 1 q of xt given xt plus 1 a of xt plus 1 comma xt. This is the first line, right? This is the first equation, I mean first before the summation or addition, and the second one will be every xt will be substituted by xt plus 1, right? So then that is equal to pi of xt plus 1 integration q of y given there was xt, that will become xt plus 1, and then there was 1 minus a, there was xt comma y, it will become xt plus 1 comma y. dy. This is equal to pi of xt plus 1, and then in the bracket I have q of xt given xt plus 1 a xt plus 1 comma xt plus integration q of y given x t plus 1 minus a x t plus 1 comma y dy. What is this thing inside the curly bracket? Proved. Whatever is inside the bracket is k of xt plus 1 comma x3, right? Proved. So therefore it is equal to pi of xt plus 1 and then transitioning from xt plus 1 to xt, and this proves the detailed balance condition or the reversibility condition. And now for this proof I did not even need the symmetry condition. So this was for any q, right? I did not use that symmetry condition like last class. So that proves that you can use this in practice because it satisfies the irreducibility criteria, the aperiodicity criteria, and the reversibility criteria, which is the pi invariance basically. Okay. So that completes our discussion on the Metropolis Hasting algorithm. And I have another half an hour, 35 minutes, which I will be utilizing for the Gibbs sampling, which again is a type of MCMC algorithm. Okay. So Gibbs sampling is also a type of MCMC algorithm. Okay. So we will start with a new topic now, although it is related to the what we are discussing now, and that is Gibbs sampling. Okay. Now, can you tell me what is can you think of any limitation of Metropolis Hasting and Metropolis algorithm, specifically Metropolis Hasting algorithm? Can you think of any limitation? Is anything coming to your mind? Look at the algorithm here, right? So here is the main algorithm is here. So look at it and tell me if you can see or think of any potential limitation of the Metropolis Hasting algorithm. That is one, and that is quite clear from this slide. You just have to imagine. Is it not possible that every time my sample is getting rejected? It is possible, right? With a finite probability, every time my sample is getting rejected. In that case, what will I have? Many of the samples will be my repeated samples, which is not a good idea. You want a diverse sample from a distribution. You don't want samples where you have 1,000 samples, but 900 of those samples are same. You will not want that. Yeah, some of those samples can be same. If you have 1,000 samples, maybe 50 samples can be same. And like that 50 you might have 3 times, like total 50 samples may be same. So one sample is 15 times, another is 20 times, another one is 10 times, one is 5 times. But overall you will want a diverse set of samples because the samples are supposed to represent your distribution. You don't want one sample repeated 1,000 times, correct? And that is the possibility in Metropolis Hasting algorithm, because every time if you go into else, it will be the previous sample, correct? And therefore, it is important to report the acceptance ratio along with Metropolis Hasting algorithm. So that means how many times you are accepting a new sample. Because if your acceptance ratio, for example, let's say is 1%, that means what? If you draw 1,000 samples, 900 of those samples are, or actually 990, I think 1%. So only 10 samples are new, other 990 are same or repetitions. So that's not a good acceptance ratio, right? 1% is not a good acceptance ratio. So one of the limitation of Metropolis Hasting, and also Metropolis, I am not writing it, whatever limitation Metropolis Hasting has, Metropolis will have the same limitation. Okay. One of the limitations of Metropolis Hasting is that the final samples may not be diverse, right? That is the potential problem with Metropolis Hasting. Now, even if most of your samples are getting accepted in Metropolis Hasting, that is generally a bad thing, because in that case probably you are stuck in one mode and you are not getting enough. So it is said, and it's a thumb rule, that the ideal acceptance ratio for a Metropolis Hasting algorithm is between 0.28 to 0.4. So if you are getting acceptance ratio between 0.28 to 0.4, you have a good proposal. Okay. So that is a thumb rule kind of based on observation. So ideal acceptance ratio is in 0.28 to 0.4. So if you are getting this kind of number, then your algorithm is actually performing quite good, probably the best. Okay. If you are getting more than that, there are other challenges that you might face. If it is less, then it's very slow. Okay. Gibbs sampling actually is an algorithm that remedies this. In Gibbs sampling, you get diverse samples and without compromising on the, or rather with a acceptance ratio of 1, all samples are accepted. Okay. But Gibbs sampling is also a Markov chain algorithm. Okay. So Gibbs sampling addresses this issue. I am not saying, remember, I am not claiming that Gibbs sampling is better than Metropolis Hasting. No, I am not doing that, because Gibbs sampling has its own limitations, which we will see later. But this particular limitation of Metropolis Hasting is addressed by Gibbs sampling. Okay, don't think that Metropolis Hasting is worse than Gibbs, because in many cases Gibbs does not work, Metropolis works. Okay, but there are scenarios where Gibbs is better, and if you can use Gibbs and Metropolis algorithm, then it's better to use Gibbs, if you can use, and that is a big can. Okay. So just to give you a high level idea of Gibbs sampling to start with, Gibbs sampling was devised to sample from high dimensional distribution. In other words, Gibbs sampling you cannot use if you have one random variable. At least 2 random variable is what is needed for using Gibbs sampling, at least 2. Okay, and it can be as high as possible, but at least 2 is what is needed. High dimensional distribution. Okay, and how does it work? It works by drawing sample from the conditional distribution. So here the idea is that if you have a distribution from which you cannot sample, but if you compute the conditional distribution, from there you can easily sample. That is the place to use Gibbs sampling. So Gibbs sampling is specifically for distributions that are intractable, but the conditionals are tractable. Clear? So the conditionals you can sample from, but the total distribution you cannot sample from. If that scenario arises, then use Gibbs sampling. Clear? So Gibbs sampling uses conditional distributions to sample from the target. Okay. So that is the whole idea, which also means that there is some mathematics involved here, because you have your target, you have to do the mathematics and find out what the conditional will be. And if it is not Gaussian, the conditional may not be Gaussian, right? So if you can find the conditional, and the conditional is easy to sample from, but the joint is something that from which you cannot sample, then you use Gibbs sampling. I am repeating this again and again. Okay. If joint is not intractable, you can directly sample. If joint is a multivariate Gaussian, that's tractable, just sample from it. Why will you go through Gibbs sampling? In Gibbs, see, the idea is that if joint is tractable, let's say joint is multivariate Gaussian, can you use Gibbs for that? Yes, you can. Will you use Gibbs for that? No, you will not. So the idea is that you will not use it, you will directly sample from it. So yes, the second is that in that case you can still use Gibbs sampling even if the joint is not intractable, but you will not use Gibbs sampling. Okay, clear? So let me write down the Gibbs sampling for two variables. That will make things easier. And then we will try to understand it and try to generalize it. Okay. So Gibbs sampling for two variables. And remember, 2 is the minimum number. You cannot use Gibbs sampling if you have one variable, because then there is no conditional. So what to conditional? Okay. Now you will have a target, right? Let's say my target is the distribution from which you want to sample. Let's say that is pi of x1 comma x2. Okay. So that means this is the distribution from which you want to sample. Okay. So this is not part of the, this is a target. So this is not the algorithm as such. Okay. But given this target, you have to compute. The first stage is do mathematics. Okay. The first step is compute pi of x1 given x2 and pi of x2 given x1. So it is an assumption that you can compute this thing. If these things are not something that you can compute or calculate, then you cannot use Gibbs sampling. Yeah, Gaussian. Suppose my target is a Gaussian, so x1 and x2 are jointly Gaussian. So that means I should be able to compute probability of x1 given x2 and probability of x2 given x1. In Gaussian case, both of these will be Gaussian. Okay. But generally it's the opposite actually. Generally we realize that we can work with things where naturally these things are known to us, but the above is not known to us. Example, likelihood times prior. In likelihood, you know the conditional, but what you don't know is the joint. One example, right? And there is a whole area of graphical model where you work with conditionals. So the conditionals are known to you, but the joint is not. Okay. Okay, so compute this thing. Okay. Even hierarchical prior and all those things will realize that we know the conditional. Okay. Okay, so I will assume that we have pi x1 comma x2, that is something that we want to sample from, and pi of x1 given x2 and pi of x2 given x1 are known to us, and you can sample from them. So computing them and knowing them is one thing, and to be able to sample from them is a different thing. Okay, so you can sample from them. Okay. So now, with that background, the algorithm starts. So the input to the algorithm is, so there is some background mathematics that I am assuming you have done. So you have to do that background mathematics before you, then you will come to the algorithm. Okay. The input is same as Metropolis Hasting. What were the inputs? Length of the chain, and then there is a proposal. There is no proposal in this case. So only the length of chain, because your proposal will be those conditionals. So length of chain. By the way, I am using this terminology length of chain in the context of Markov chain, because it is the length of chain, Markov chain, but it's basically the same. Okay. And then what was the first step in Metropolis Hasting? You have some initial condition. Okay. Same thing here. So suppose you have x0, which is basically equal to x10 and x20. This is my initial thing, right? So now here is how it will work. So you set xt to be x0. Okay, you may not, but I am writing it like that to generalize the thing. And then you will draw x t plus 1 from probability of it can also be 2 actually, but I am drawing 1, so I will write it like that. x1 given x2 t. Okay. So basically, and this conditional I have already assumed is known to me. Okay. And whatever you see in the superscript basically denotes the chain number. That's all it does. So that has no meaning actually. Okay. Next, you will draw sample of x2 t plus 1, and that will be equal to, you will draw it from where, this is the notation actually, the notation is wrong, because it's a sample, it's not equal to. Okay, this is the notation. Pi of x2 given x1 t plus 1, not t. So the sample you just generated here will be used as a conditional. Okay, done. That is your algorithm. Keep on doing for t equal to 1, t plus 1, t plus 2 up to n. Done. Okay, so the sample you got is basically, if I have to write, so the sample you got is x t plus 1 is equal to x1 t plus 1 comma x2 t plus 1. Okay, clear? So now you tell me what is the transition kernel for this, because I said this is a Markov chain. So if it is a Markov chain, what is the transition kernel? So transition kernel for Gibbs. So basically what I want is k of going from xt to xt plus 1. Previously I was writing it in the subscript, now I am writing in the superscript to be consistent with the notation. Okay, you can write it in the subscript as well. Okay, so tell me what is this probability, or it is a probability, so yeah, what is this equal to? From the algorithm you should be able to tell me. What is the transition kernel? Don't go to Metropolis Hasting, you will not get any similarity with that. Just a clue I am giving. Just look at the algorithm. Metropolis Hasting and this has no similarity. Okay. Think about the algorithm. How are you going from xt to xt plus 1? Transition kernel is what? How are you transitioning from xt to xt plus 1? That's the transition kernel. So how are you going? How are you going? by drawing sample from conditionals, right? So what will it look like? So first, what are you doing? You are drawing sample from pi x1 t plus 1 given x2t multiplied by pi x2 t plus 1 given by x1 t plus 1. That's all you are doing, right? And there is no acceptance here because everything is getting accepted. So that's why there is no A. Okay. Just look at the algorithm. That will give you the transition kernel. So what did I have? To start with, I had xt. That means I had x1t and x2t. I use x1t, x2t to generate x1 t plus 1. That's what you see here. I used x2t to generate x1 t plus 1. And then I used x1 t plus 1 to generate x2 t plus 1. That is my kernel, right? Clear? Now, what I need to show? If this has to be a valid Markov chain from where I can sample, it should satisfy the same three criteria. What are the three criteria? Irreducibility, aperiodicity, and detailed balance. The good thing is that for this I will not show detailed balance. For this you can actually show pi invariance is directly satisfied. So with Gibbs sampling you do not need to go to detailed balance. You can show that pi invariance is directly satisfied. Okay. So this kernel, this satisfies pi invariance. Now who will remind me what is pi invariance? Remind me what is pi invariance. You have to go a little bit back. So let's see. What was the pi invariance criteria? Pi of x t plus 1 is equal to integration pi of xt k of xt comma xt plus 1 d of xt. So that is pi of xt k of xt comma xt plus 1. Again I wrote in the, okay, I should write at the top to be consistent. Remember, whatever I am writing at the top superscript for Gibbs is equivalent to whatever I wrote at the subscript for Metropolis system. Okay. Integration of d of xt should be equal to pi of x t plus 1. Okay. So now to prove it, what will I do? I will take the top expression, substitute in place of k, and then do mathematics. Can I repeat the top one? So look at the algorithm. What are you doing? What is the kernel? First of all, what is the definition of kernel? Kernel, basically the definition is the probability of transitioning from xt to xt plus 1. Now look at the algorithm. How am I going from xt to xt plus 1? I have xt, equation number 2, not equation, line number 2 or algorithm step 2. Then what am I doing? I am getting x1 t plus 1 by drawing sample from that conditional. I am getting x2 t plus 1 by drawing sample from that conditional. So my transition kernel should be the product of those two, because that's how I am transitioning. If I have to go to you, I will go from you to her to you. So that's what I am doing. I am going from here to there and from there to here. That's what it is. Okay. So now to prove this, I will just substitute the above expression into this, which is equal to, so consider the LHS. So I have integration of pi of xt, and instead of the kernel I will write whatever is there at the top. So is pi of x1 t plus 1 given x2 t, pi of x2 t plus 1 given x1 t plus 1, d of xt. Now you tell me what is this xt equal to? What is this xt? xt is nothing but it's a joint x1t comma x2t, right? Xt is, that's what xt is, it's a joint distribution. And similarly here, xt is d of x1t multiplied by d of x2t. I have two variables. So that means that integral is actually two integrations. I will repeat, x is a vector. So, and in my case, it's a two-dimensional vector. So that means the integral will be two-dimensional integration. It's not a single integration. Xt will become x1t, x2t. And even inside it will be x1t, x2t. Clear? This is equal to then integration pi of x1t comma x2t, pi of x1 t plus 1 given x2t, pi of x2 t plus 1 given x1 t plus 1, d of x1 t, d of x2 t. Okay, clear? Now, which of these expressions are having x1 and which of these expressions are having x2, and which one is having nothing? Let's start from the last one. What is the last one? T plus 1. Is it a function of t? No. So that can go outside the integral. Second one, what is it? It is function of only x2t. Is there any x1 t? No. So that is only integration will be only over x2. First one, the integration will be both over x1 and x2, right? So we should start with the first one. So this is equal to whatever is nothing is there, I am going to bring it outside. So pi of x2 t plus 1 given x1 t plus 1 integration, okay, pi of x1 t plus 1 given x2 t integration pi of x1 t x2 t, and then this is the only one that is integrating over x1, and then you have d of x2 t, right? See what I have done? The last term is not a function of either x1t or x2t, so it goes outside the integral. The first term is function of both x1t and x2t, so it is the innermost term inside both the integral. The second term is only inside x2 integral. Clear? So now you tell me what is the innermost integral equal to? What is that term? You should be able to tell. That is one of the basic law of probability that we are using throughout this course. Some law. So whatever is integrating over, the other one will remain, right? So this is equal to pi of x2 t plus 1 given x1 t plus 1 integration pi of x1 t plus 1 given x2 t multiplied by this whole bracket. Let me change another color. This whole thing that you see, this is equal to pi of x2 t. So multiplied by pi of x2 t and then d of x2 t. This is equal to pi of x2 t plus 1 given x1 t plus 1. What is the term? The two terms inside, if I do a product, what will I get? x1 t plus 1 comma x2, product law, pi of x1 t plus 1 comma x2 t d of x2 t. So now you tell me what is that integral equal to? Given multiplied by pi of x1 t plus 1, again the sum law, and then what is the final thing you are getting? The right hand side, what we are, pi of x t plus 1. This is equal to pi x1 t plus 1 comma x2 t plus 1 is equal to pi of x t plus 1, and that proves the pi invariance criteria. Okay, clear? So the detailed balance criteria we did not satisfy, we satisfied directly the pi invariance criteria, right? Now, but that is not enough, there are other criteria also, right? What are the other two criteria? Aperiodicity, that is automatically satisfied because it's a conditional random distribution. So there is no acceptance in this case. Last time I said that because you are starting from some deterministic value. So because of that, even if it is periodic, you will still get rejected or accepted with a finite probability. In this case, it is not like that, but because the distribution from which I am sampling is random, so that will not be periodic. But the important thing is irreducibility. And irreducibility is not guaranteed in Gibbs sampling. Not guaranteed. So you have to be careful. You cannot blindly use Gibbs sampling, because in that case you might be stuck, and that is one limitation. Okay. Irreducibility is not guaranteed. Okay. So now let me give you one example to show that. Suppose this is my x-axis or x1 axis. This is, so I have a bivariate distribution, okay, and this is the contour of the distribution. Okay, this is a contour. Can you tell me what is this distribution equal to? What is the PDF of this distribution? What distribution will look like this? Uniform, 2D uniform in x1 and x2, right? But we don't have a uniform distribution, we have distribution something like this. This is zero probability distribution, this is zero probability distribution. That means the probability mass is only in this area and in this area. Okay, the other areas have no probability mass. So if you think about in 3D, this two hashed area will go up, the others will be zero. So think about two squares which are diagonally placed. The other two diagonals are zero probability. Okay. Now what will, for such a distribution, for any distribution, what does irreducibility means? Because I explained it in terms of state, but in such a continuous variable, what do you think irreducibility means? It means that you should be able to sample from any area that is having a positive probability mass. Irreducibility means you should be able to sample from any area that has a positive or non-zero probability mass. So that means you should be able to sample from the two diagonals. Correct? So now think about how Gibbs sampling works. What is the first step of Gibbs sampling? Conditional, suppose I calculate it, then you will start from some point. Let's say that point is this one. Okay, this is my x1. Then how do you get x2? You will draw a conditional. So conditional means what? You will draw a straight line. This is your conditional distribution, should be like this. Now you draw any sample from this conditional. Where will you get the sample? Only in the shaded area. Can you get any sample in the zero area? Because there is zero, you will not. So suppose I get a sample here. So this becomes my x2. Right? Now next is I will again draw x1. So that means I will look at the conditional, which is, where will I get x1? Again somewhere in the shaded area. Can I ever go to the top shaded area? So what happens? This becomes a irreducible case. So using Gibbs, you will never be able to sample from the top right. If you start from top left, and if you start from top right, you will never be able to sample from bottom left. So if you start from bottom left, you will be stuck there. You cannot go to top right. And if you are at top right, you can never go to bottom left. Until and unless you are extremely lucky and you end up at this point as a sample. But that is almost equal to 0 probability. Okay, because that's a point, and we know that in continuous the probability of landing at a point is equal to 0. You have to always look at the area. Okay, so that's a very extreme case. So what to do in this kind of scenario? In this scenario, what the solution is, so this is a reducible for Gibbs. So the solution for this is that you have to do a variable transformation. So the solution is do variable transformation. And if you do variable transformation, and under some variable transformation, it might become like this. So there is a specific transformation for which this happens. And if this happens, then you are good. So basically, this is your probability mass now. Okay. I am not telling you what transformation, but let's say there is a transformation for which it becomes like this. Then you are good. Then you can now use Gibbs sampling. So the take home message is that to use Gibbs sampling, you have to be little bit aware of the things you are trying to sample from. Otherwise, it might happen that in some cases, not always, might be your target distribution is reducible, and so you might have to do some variable transformation. Clear? So I will stop here for today. Next lecture, which is after your exam, Thursday, we'll first spend 5 or 10 minutes on the Gibbs sampling part to generalize it to n dimension. It's actually straightforward, not take more than 5 to 10 minutes. And then we'll talk about Hamiltonian Monte Carlo, and we'll also talk about sequential Monte Carlo. And that will be the end of the sampling part. Okay, so next lecture will be the last lecture on sampling, where we will first talk about, wrap this up to summarize. There are many observations here, right? And then we'll talk about Hamiltonian Monte Carlo and sequential Monte Carlo. We'll talk about those two things, and then we'll talk about some ways to combine. So you can combine Metropolis testing with Gibbs. Those options are there. So we'll talk about that also. Okay, so basically we'll wrap up our discussion on sampling in the next lecture. Homework 2 is ready. I've just not uploaded it. I'll upload it today. I wanted to finish Gibbs before I upload it. So I will upload homework 2 today. Okay, and that will also, obviously your exam is on Moodle. So that will not help you that much, but you can at least see what kind of questions can be there, let's say in the majors from sampling, because it might seem that everything is like programming here, which is, but there can be theoretical questions also. So that will become clear when I upload the homework 2. Yes, the syllabus is till now. Okay, thank you.